And so our last talk now is by Ciprian Bonciocat, who is going to speak about degenerate Lagrangian intersections and parametric Floer homotopy theory. So
Yeah.
I don't know if I see you. Oh, yes.
Can you see
All right.
I'm sharing the
Yeah,
screen. Can you see
all
the,
good.
okay.
On my screen, it's all good.
Okay.
So please go ahead, Ciprian.
Yeah. So thank you very much for having me. This talk will be way less analytical than the last two, I guess. Um, so yeah, be talking about the general Lagrangian intersection. So like the general null conjecture type questions, and I'll briefly introduce Floer homotopy theory, and I'll explain how you can use this to obtain lower bounds for the general Lagrangian intersections. And this work was joined with Kenny Blakey, who is here in the audience. Okay, so yeah, so the setup will be we have a symplectic manifold, two closed embedded Lagrangians, although you might be able to generalize the techniques in this talk for more general settings. So let's briefly recall the classical Arnold given all conjecture. So this states that, well, in the case that the two Lagrangians intersect transversely, and one of them is a Hamiltonian isotopy of the other, then we have this lower bound, which is reminiscent of the Morse inequalities. So the cardinality of the intersection should be bounded below by the sum of the Betti numbers of the common homotopy type. So I'll just briefly recall, I'm sure for many of you, this is very standard. So some classical results in this direction. So Andreas Floer with his revolutionary paper showed, at least in the spherical case, that this is true using Floer homology. So it's basically just Morse inequalities for a carefully constructed notion of Morse homology for infinite dimensional manifolds. And then there have been many results. So I probably can't do justice to everyone, but so just to mention one cute application is RPN and CPN, and then Fukao Taono generalized this for semi-positive manifolds. And there's been a lot of other work, but I'll enter myself to these. So now I want to shift the direction a little bit, and so the classical Arnold-Givenel conjectures for transverse intersections, but one could ask, what if we drop this assumption, right? So then a naive Morse theoretic approach wouldn't work anymore. So there have been some results in this category. So there's some kind of theoretic Luster-Nix-Schnirelmann theory that can be used to give lower bounds in terms of cup length. So Hofer and Floer, I think, independently sort of came up with this, and this can also be generalized in generalized cohomology theories by a more recent result, Hirschi and Porcelli. So I want to outline first a general strategy for how to approach this type of question. So the plan consists in the following. I just put 4 steps. So the first step is to find some sort of global invariant X. So this should be like some kind of algebraic invariant. And it should be filtered. So when I didn't say this here in the slide, that it's not too crowded, but we're going to assume that we only have finitely many intersection points, right? If there are infinitely many, then obviously, the lower bound will hold. So if we have finitely many intersection points, I want the invariant to have a filtration whose associated gradient is given by some kind of local version of the global invariant at a point. So far, this is just fake philosophy, but I want to have this. And then crucially, is the most crucial step is I want to find some special property P that the local invariant satisfy that maybe the global invariant doesn't, right? And for this theory to be useful, I also want to be able to compute the invariant. So the invariant should be something computable in terms of some algebraic topology of symplectic manifold of the two Lagrangians. And then finally, the claim is now you should well, you can always get some kind of abstract bound, lower bound, but basically the idea is the property P constrains what kind of associated gradients my invariant can have. And so in particular, you want to be able to argue algebraically that X does not admit the filtration with associated gradient satisfying property P unless the length is sufficiently large. And then this will give you a lower bound on the number of intersection points. So I'll stop here to see if there are any questions. I guess this is very important to understand this plan because I will be using it several times, right? So I have a global invariant, local invariant that satisfies some extra property that the global one doesn't necessarily satisfy. So as a warm-up example, I think this is sort of classical, but I don't know who wrote it down first, but I learned this from Kenny's paper. So I'm going to assume for simplicity that M is Liouville and L is exact. So the global invariant will just be Floer homology, but equipped with this cap product, cap action. So the claim is that the cohomology of the Lagrangian acts on Floer homology. And this is basically, I think there are many different ways of viewing this. The one that I like to think of the most is you can represent cohomology classes in L by like a Poincare cycle in the manifold, and then you define the action by counting intersections of the moduli space of Floer trajectories with this cycle. So if you're in the right dimension, then that's a zero-dimensional manifold. Then again, you can count and get a number.
Ciprian, what is HF
yes.
star of relative to L?
Yeah, so I'm using this note. I guess it's more common to say L0 and L1, but I'm using this notation to mean, so there is a notion of Floer homology for only one Lagrangian, and you have to pick some Hamiltonian deformation. So I'm assuming that to be implicit in the notation.
I understand, but M is just to indicate the ambient manifold.
Yes, yeah.
Okay.
That's right.
Good.
Yeah. Okay, and then so we have this global invariant. Again, you have this filtration by action, and the standard Posiak type argument shows you that you can compute the Floer homology locally at some kind of Morse homology. So now I have to tell you what the special property that these local invariants satisfy, and the claim here is that this cap action becomes trivial in the sense that any element other than the identity will act zero on the graded pieces. And this is because in this Pozniak deformation argument, you can ensure that all of your homomorphic curves are sort of very small. So they're all, in particular, they're embedding factors through a ball. And since the ball is contractible, all the higher intersection numbers will vanish. So, and then also computability. So I guess this is where I assume the Liouville and exact, so that you have this isomorphism with classical singular homology, and then you get this bound. So you get the lower bound by the cap length. So this is like it's kind of, to me, this is always kind of confusing, but it's like, so I formulate it as the smallest k such that all iterated length k cap products are zero, where you iterate over all alpha other than the identity. So this is a warm-up example to illustrate the idea, but we will use more complicated invariants in the talk. So now let's switch gears and talk about Floer homotopy theory. So this is kind of a very technical subject, and I really don't have time here to give a proper introduction, so I'm afraid I'll just have to black box a bunch of tools. So the idea is to replace classical rings with a sort of a homotopical upgrade, and then similarly chain complexes to have some sort of lift of that. So, I mean, if these words are scary, it doesn't really matter what they are. We just need to sort of know their formal properties. So a ring spectrum is just a generalization of a classical ring. That's how you should think about it. So in particular, classical rings are ring spectra. And also I should say they're homotopical in nature. So this is not really purely algebraic, but yeah. So the point is we still have a derived category of our modules. So they're not chain complexes, but they sort of behave formally very similarly. And we have this functor from spaces to the derived category, which we call the R homotopy type. So if you hear me use the notion, the words homotopy type, this is kind of the motivation. Because otherwise, ring spectra is sounds like something very abstract. But so we have some way to given a space to associate an algebraic object in this category that we call the homotopy type. And there are many classical invariants that you can recover from this. So there's a generalization, or not, there's an appropriate notion of homology, which now I guess I'm calling phi n instead of hn. So phi n of x is just maps from r in degree n into x. So I'll just give you two examples. So for classical rings, the derived category recovers the usual derived category. And R tensor X is now it's just the chain complex, and it turns out it's just the singular chains on X with coefficients in R. So pi n of X would just be homology. Or pi n of R tensor X would just be homology with our coefficients. And then a more interesting example is what's called the sphere spectrum. So this, you should think of it as playing the role of Z. So it's the initial ring spectrum. And it's like the strongest theory. So if you can define your theory over S, then you can define your theory over any other ring. And S tensor X has a nice significance. So it remembers, at least let's say when X is a finite W complex, it remembers the stable homotopy type in the following sense. So if X and Y are two spaces, we say they're stably homotopy equivalent if some common suspension of them is if we take suspension, find a number of times if they become homotopy equivalent. So it's still kind of a very down-to-earth notion. Okay. So now let's get to Floer homotopy theory, right? So the goal or the question is, can you define, if I give you a ring spectrum that is not classical, is there some way to define Floer theory over this ring? So I'm using it here as the coefficient. So I want this, I'm calling it CF bullet as opposed to CF pad because it's not really a chain complex, but it kind of wants to be morally. So can we build such an object in the derived category over a non-classical ring? So there have been, several approaches to this in the literature. I guess the most classical one is Goenjo and Siegel in their 1995 paper, and there are more modern approaches based on the categories. So like Abu Zaid Blomberg, it's like a big project that's still ongoing. So I'll briefly discuss what input you need. I will not talk about the construction at all because it's kind of impossible in this time span. But so one thing to note is, so usual or ordinary for homology only requires moduli spaces of dimension 0 and 1 in order to build the chain complex. Here, you potentially need the compactified moduli spaces to be smooth manifolds with corners for all dimensions, so not just 0 and 1. And let's say in Lagrangian theory, this I think it's kind of settled. So there are some exponential estimates due to Fukao Taono that then give you large proofs in his thesis that you can arrange the moduli spaces to be smooth manifolds with corners. And I think there were some hiccups and some mistakes, but they're supposedly fixed in more recent work of Porcelli and Smith. There's that. And then there's something that is sort of analogous to a brane structure. So even in order to be able to define Floer homology over Z, you need some additional data on the two Lagrangians. So here, I'll briefly explain what this is. So here, the brane data will be a choice of null homotopy of a certain map of spaces. So the domain is what's called the pad space. So the pad space is just the space of pads in M with the beginning at L0 and ending at L1. And this has a natural map to U mod O. So U mod O is the Lagrangian Grassmannian, and it turns out you can make sense of the formal difference of TL0 minus TL1. So sort of as an element of K theory, and you can upgrade this to a map to U mod O. And then this rest of the stuff you don't really need to know what it is. It's just some, the ring spectrum shows up here in the codomain. So we have some map, and if we can null homotope it, then we can define theory over R. So this is kind of folklore. I mean, in the sense that like the ideas are not that complicated, but the the execution is like a bit painful. So I provided a sketch of this in my paper, and also asked when the Deschmuck-Pilak also have something about this in their paper. So yeah, so this is the input that you need, and I'll just give you one example. So when the ring is the integer, so a classical ring, GL1 of Z is just E mod 2. So then the space is an Albert-MacLane space that classifies H upper 2 as E mod 2 coefficient, right? And that shouldn't be surprising because, classically, or the easiest criterion to state for being able to define coefficients over Z is that the Lagrangians are spin. So in particular, you recover this more complicated. So this is the most, I guess, the most general assumption. So that the W2 of the difference of the tangent models of the two Lagrangians should be 0. Okay. So I know we don't have much time, so I guess I will sort of speed run through this. So when R is the sphere spectrum, the point is the cohomology, the Floer cohomology can be endowed with an action of the Steenrod algebra. So we have Steenrod squares acting on this. And Blakey shows in his paper that the local invariants have some kind of vanishing condition for Steenrod squares that maybe you wouldn't expect. So it's like, I didn't put the exact bound because it's like, usually it's like about half the dimension of the Lagrangian, but in certain specific dimensions, you can do even better. So like for dimension 7, you can do I equals 2, I think. So, and then again, you need computability of the invariant, but it turns out that if you have a connected clean intersection in the same like Liouville exact setup, then the cohomologies agree as modules over the Steenrod algebra. And therefore you get a lower bound very similar to the cap length product, except now it's like an iterated Steenrod square bound. And Kenny uses this to show as an application that so it turns out you can embed CP2 in S7, and this is like the smallest dimension of a sphere that you can embed it in. And then you should plumb two T star S7s along this embedding. You can show that the two zero sections must intersect in at least 2 points. I think even a distinct action, if I'm not mistaken, after Hamiltonian isotopy. So now I want to get to the strongest invariant, and this is the main result that Kenny and I figured out. So we massively improved the previous statement. So we showed that for any two, I guess closed smooth manifolds, connected smooth manifolds L0 and L1, and any plumbing along an oriented submanifold, again, the two zero sections must intersect in at least 2 points after Hamiltonian deformation. And this, we probably don't need the orientable assumption, but it was just a lot easier to prove. And I don't know, we kind of ran out of ideas for how to do this in general. We had some ideas, but they would require a lot more details. So, and I want to mention as a corollary of this is, you might ask, why do you care about this kind of plumbing? Well, turns out it's always a local model for a clean intersection in any symplectic manifold. So that means in any symplectic manifold, if you have some Hamiltonian deformation where the two Lagrangians intersect at only 1 point, then it must escape any such tubular neighborhood. So it's like it tells you that the Hamiltonian deformation needs to be large in a certain sense. So the invariant that we use here is this parametric for homotopy type. So what do we mean by this? So remember we had this polarization map in so as input you needed a null homotopy of this, but there could be many such null homotopies, and those could give you potentially different invariants. So what we do is we consider this space script B of all such null homotopies, and we build a parameterized Floer spectrum over this base. So this is a classical notion in stable homotopy theory. So this is more than just all the fibers. You should think of it as kind of like a fiber bundle of spectra. And then, so this was the global invariant, and the local property that's crucial here is that the local parametric Floer module at each intersection point is constant. So it's like, as a bundle, you should think it's like trivial, right? And the reason for this is, again, in a Pozniak neighborhood, all the homomorphic strips sort of factor through a contractible, they factor through a ball, right? And therefore, you kind of don't see the. I mean, the problem is I didn't show you the construction, but basically, you don't really see the effect of this choice at all there. And yeah, so then all we have to do is show that the parametric Floer homotopy type that we get is non-constant as a family over the base, and that will give us the statement. And I guess I'll end here, and I have more details if people want to, if they want to ask questions. So the way we show that this is non-constant is we produce non-trivial higher monodromies, right? So monodromy is like you just restrict your bundle to S1. But here, because this is like a homotopical setting, we can actually look at something over Sn, right? And if we show that this family is non-trivial over some Sn mapping into the base, then in particular we win. And we translate that condition into some non-vanishing of some cohomotopy class of C. So cohomotopy theory is like the cohomology theory associated to the sphere spectrum. And this is the only place where we need the oriented assumption on C. And as I said, I expect this is true even for non-oriented. But yeah, this is what we're able to do. So yeah, thank you. Thank you for your attention. I think I'm out of time, right?
Thank you very much.
Thank you.
I don't know if there are any questions. Thanks for this talk, Ciprian. For trying to fit into little time a lot of stuff. So maybe there are some questions. So maybe I have a question. So you mentioned this fact that you need that the compactification of the moduli spaces of all dimensions to be smooth manifolds. And that this appeared in Tim Large's thesis, but maybe there was like a little gap there. Is this what did I understand?
Yes, and this is sort of a second-hand information, but yeah. So I think Portelli and Smith solved this. Yeah.
Is Porcelli Smith thing available now, or
yes, they have I think 4 papers already. I think the first 2 already dealt with. There's a lot of stuff that's hidden under the rug there, so it's too far away. But yeah,
it's about 20 years ago. So we had some other variant of using high dimension moduli spaces with Barreau that we wrote in around 2004. The paper appeared in 2007, but in any case, this was a significant issue at the time. What's the structure exactly of the compactification of the moduli spaces. So I thought in the meanwhile that the team had solved it. But okay, so
yes, maybe. I mean those are some minor technicalities about yeah.
Okay, I mean the subject is full of minor technicalities that
yes,
somehow in fact are never solved. So because in fact they looked minor, but they turn out to be less minor. In any case, but I hope it's solved indeed. I mean, I have no reason to, believe it. So it's very interesting. I don't know. Maybe there are other questions.
So when you said that Hamiltonian isotopy should be large, can you quantify it, let's say, in the sense of Hofer's metric, or I mean, with some symplectic measurement?
So I didn't try to do this, and I should preface this by saying I'm not really a symplectic geometer, so you would certainly know better than me. But so yeah, the question is how large can you make this standard neighborhood of a clean intersection, right? So it's that kind of question. So like even if you got just one Lagrangian, what is the biggest Weinstein tubular neighborhood that you can fit inside the manifold?
So for one Lagrangian, there are techniques now for this of some sort, because you can use filter versions of all the all the invariants, and then they'll give you an estimate of how much, you know, how much energy you need to do each operation. So, but okay, combining filtrations, I think, with the stable homotopy theory side, it's another. I think it's one more level of difficulty. So.
Yeah, I'm actually not sure that you actually need to control the size of tubular neighborhood. Yeah, so the proof which you have in mind probably goes through this. Yeah, but there could be some other argument which says that if isotopy is small, so then it's, I mean, you don't have enough power to destroy this extra point which you have, right? So if it, for instance, corresponds to some bar, right, in the barcode, so you simply cannot destroy it by small. So, I mean, yeah.
Yeah, it sounds interesting. Yeah, but yeah, one would then have to combine this with this parametric thing.
Right. So, I don't know, maybe there are some other questions. Still have a little bit of time. In any case, in the meanwhile, I want to thank all our three speakers of today. These talks are some of the most exciting we see. There are lots of things happening in a brief amount of time, and so it's very enjoyable and interesting for all. So thank you very much for all three. We still have a little bit of time, maybe, if there are more questions. I'll press my clap button again.
Okay, thank you very much.